let's talk about fission. Fission is the splitting up of large atoms into smaller ones. One of the most easy to split up nuclei is uranium-235, an isotope, a rare isotope of uranium, but one that if I take a neutron, and this neutron could be going really any speed, particularly if it's going very slow, and if it hits uranium-235, this is the before picture. The after picture is that the uranium has split up into two separate pieces. These are things we call fission products. All right? These fission products. And these fission products are moving really, really fast. Because after all, in this process, I took something that was relatively stable, right, and turned it into things that were more stable. Another way of thinking it from the E equals mc squared is that this side weighs more and this side weighs less. And that energy, that mass difference, turns into energy. The energy is manifested, is shown by the fact that these things are moving. Whatever they're embedded in, the fuel pellet that they are stuck in, gets hot. But there's one other really key thing about fission, is that I don't just make the two splits of this, I make some extra neutrons. 2.45 is the average number. I've drawn 3 here, and these things are moving very fast also. Fission splits up uranium into fission products. It makes the matrix it's held in warm because they're moving, and it makes extra neutrons. And that's the key, because you see these neutrons could go and cause more fissions. We could get a chain reaction. There's one key thing here, though. Remember how I said that this neutron was slow? And these neutrons here are fast. I don't just mean a little slow and fast. These things are going at something like 1,000,000 electron volts. And these, the ones that can actually cause the fissions, are going more like, on the order of 0.01 eV, 100 million times slower. There's a really important graph. I'm going to draw it for you now. And it's a graph on this side of the chance of fission. Cross-section. And up here is 1. And that means it'll make fission. And it's a log graph. So here it's 1/10. And maybe here it's 100th. And maybe down here it's 1,000th. Not very likely. That's the chance of making a fission, a chance of this reaction happening. Along here is the speed of the neutron. Right up here are the fast ones. These are the ones that are going 1,000,000 eV, the ones that are created after this fission event takes place. And this is also a log graph. There's 1,000,000, there's 100,000, there's 10,000, there's 1,000, right? There's 100, there's 10, there's 1. Here's 0.1, here's the 0.01. These are the slow neutrons, and the chance of those slow neutrons making a fission is very large. And the chance of the fast neutrons making a fission, all right, take a look over here, is very small. Slow neutrons create new fission events. Fast neutrons are the ones that are created. So now let's think about the chain reaction. If I want these neutrons to come and hit more uranium and have it actually fission, I've got a couple ways to do it. One is I could just have a lot of uranium around. I could make the whole thing out of solid uranium-235. That's called a nuclear bomb. And if I was at 90% or more uranium-235 and the only thing these neutrons could ever hit, they would bounce around uranium, bounce around, bounce around. Eventually, they would cause another fission and we'd get more out. And that eventually may be nanoseconds, right? Because they're all next to each other. We're going atomic scales. And indeed, that would make a nuclear explosion. You would have your mushroom cloud. But if I made a much less fuel density, not 90% uranium-235, but like a normal nuclear reactor, which is only around 3% uranium-235, that's little enough uranium that these fast neutrons will be lost. They will leave the reactor. They will get absorbed or go on somewhere else, and you will have absolutely no chain reaction unless you somehow slow down the neutrons. You need to take these fast ones and turn them into slow ones. You need to moderate their speeds. You need to slow them down. And the stuff that does that is called a moderator. There are two things you could use to moderate successfully. One is water. And you can see in this demo that we are now slowing down neutrons with water. And the reason it slows down is because the hydrogen atom and the neutron itself are similar mass. So just like the two ping pong balls, if I have two ping pong balls hit each other, one slows down or one speeds up a little. They share the momentum. If, on the other hand, I was taking a ping pong ball, the neutron, and it was bouncing off the wall or bouncing off bowling balls, it doesn't slow it down at all. It's not moderated in speed. You need something to be much less massive than, say, the uranium to slow down the neutron. So, in almost all nuclear reactors, the water is the moderator. And not just any water. The very same water that you use to cool the reactor is the moderator itself. And that's a wonderful, inherent safety system. See, let's just step back a moment. What is it you're trying to do in a nuclear reactor? Make electricity. And just like using a coal power plant or an oil power plant, you use the heat to boil the water. The water then turns a turbine, the turbine spins a generator, and you have electricity. In a nuclear plant, we do the same thing. We want to boil the water to cool the reactor. So if your water is also your moderator, then if something goes wrong, if the pipe breaks, or someone turns off the water supply, or the reactor gets a little too hot so all of the water turns into steam, your moderator is gone. And if you have no moderator, the neutrons never become slow neutrons. If they don't become slow neutrons, the chain reaction stops. So in almost all nuclear reactors, if you lose your coolant, the chain reaction automatically stops. You do not need a reactor operator pressing the button. You don't need some safety system to kick in. Just the laws of physics. Fast neutrons do not cause fissions. So if there is nothing to slow them down, if your cooling water is gone, your chain reaction will cease. Now notice I said almost all nuclear reactors. The RMBK reactors, created by the former Soviet Union, Chernobyl in the Ukraine being one example of one, had blocks of graphite as the moderator. They still had water as the coolant, but the moderator was graphite. So if they lost their coolant, the moderator was still present, and the chain reaction would not stop. If you ask people, hey, well, can Chernobyl happen here? No, actually it can't. All of the reactors except the 12 RMBKs actually run on having water, the same water, as both the coolant and the moderator. If you lose the coolant, you lose the moderator. If you lose the moderator, the chain reaction stops.